Hey, biophysicist. Welcome back to another show. Today with us, we have Adegbola or Bola from Texas Tech. He's a researcher there that's recently been looking at ionic liquids. So specifically, they've trying to look at extending the time scale of molecular simulations using the time temperature superposition. So Adegbola, thanks for being on the show.
Thank you for having me on this show.
Yeah. So, let's just kind of jump right into it. So, this is kind of, maybe not particularly what you think about when you think of biophysics, but, you know, I think it all kind of ties in together, right? We all have kind of some underlying physics behind it. So what kind of got you interested in this problem to begin with?
Wow. So, thank you so much. So, let me start with this. The goal of the project, basically, this particular project actually is to measure the mechanical properties of, the material, so which is ionic liquid in this case, right? So one thing about materials generally is that materials basically, they deform at different frequencies and kind of, and the response to the material, or the response of the material to deformation is usually measured. So one thing in real life experiment is that one can measure the properties over a certain time, such as, in seconds, in minutes, and in hours. But for MD simulation, that we can do the same thing, but at a lower time scale. What do I mean? Like if the molecular structure of the material is known, one can measure the mechanical properties using simulation. But like I said earlier, computer simulation has the ability of the time scale up to microseconds. You can't compare with experimental. Experimental, you can do up to, seconds, minutes, hours. So now, to account for the difference, that the time scale disparity now between experiment and simulation, so one can use the time temperature superposition. And that is what we're trying to do. I mean, that's what actually got us interested. Okay, let's do this for ionic liquid, and let's, use time temperature superposition to account for the time scale disparity between experiment and simulation.
Yeah, so I guess it seems like it's really, really hard with simulations to have a long enough time scale. You can't just throw it to the supercomputer and come back in 25 years to finally get something.
Probably maybe in the next 25 years, we would have, computer that will have the ability, to run simulation up to, seconds, or maybe the next 20, 25 years. I mean, yeah, because in the last 10 years, 10 years back, they couldn't even do up to microseconds, and now we can actually do up to microseconds. So the field is, improving gradually, and the computational ability is kind of getting better with time.
Yeah, it's definitely improving, but no advisor wants to hear the grad student say that, oh, well, I'll have those runs done in 25 years. So I guess, let's even kind of take a step back then. So can you kind of define for us what an ionic liquid even is?
So basically, when you talk about ionic liquids, so ionic liquids are stored in liquid form. So that's just the simple definition for ionic liquid.
That's an apt name then for it then.
Yeah.
So it's just some charged group that's liquidized. Is the surrounding medium typically water, or does it depend what it's mixed in with?
It depends on what is mixed in with. It doesn't have to be. It depends. Yeah.
So it can be pretty much anything.
Yeah, okay, and it can be on its own,
So I guess, can you kind of break down this time temperature superposition then? So you said it kind of helps us look at things at a longer time scale that's more in line with experiment, but how exactly and why exactly does that work?
All right. So that's just like me explaining what time temperature superposition is. So basically, one thing is that time temperature superposition, like I said, is used to determine the temperature dependence of the rheological behavior of a polymery liquid, or even it could be any soft matter, to expand the range of time and frequency regimes at the temperature in which the behavior of a material is being studied, right? So, like I said earlier, right, sometimes even in simulation or experiment, most times it is difficult to measure the properties of materials at short time and sometimes at longer time. So in order to achieve this, like I said, one can actually, so what time temperature superposition basically is that, okay, you measure the properties of the material at different temperature. Let's say, for instance, here now we're talking about rheological properties. So we're talking about the, let's say, viscosity, elastic moduli, viscous moduli, I think several mechanical properties like that. So what one can do is that you can apply different frequencies to these properties, right? So to this material and measure their response. So in this case now, so you have, let's say, elastic moduli, for instance, on the y-axis, you have what's it called? Let's say frequency on the x-axis. Then you measure the properties at different temperature. So now, once you have the properties at different temperature, basically, you can actually collapse, right? You can choose like a reference temperature. Let's say I want to know the property I want to know is at 300 degrees C. Let's say, for instance, 300 Kelvin. So you can collapse. So I can measure maybe from 210 to, let's say, maybe 450, for instance. And there's a way I can actually collapse in such a way that everything will form just a master curve. So that is what time temperature superposition is. So, but how do we do this? Like, okay, how do I know I can do this, right? So one thing there are some criteria we have for you to apply TTS. And basically, the first thing is that you must have exact matching of shear at adjacent cores. That means the relaxation time at each temperature must have a certain strength, like a certain shape, right? So once they have like almost the same shape, then that means the shape tells us how the relaxation time scale changes with temperature. So that's the number one criteria. So once you have this, once you notice this kind of trend, like the same trend at different temperature, then you might kind of look into, applying TTS to form like a master curve.
So I guess in some sense, by running it at a higher temperature, you need to see more or less the same behavior. If I were to take you or me and, throw us in a hot sauna, you wouldn't expect to see the same behavior out of us?
Yeah, basically. So they have to show like the same strength at those different temperatures. So there are still some other criteria. That's just the only one. There are still some other things which you have to consider to make for you to actually confirm, oh, okay, TTS actually work for this.
So yeah, I guess I kind of understand that then as essentially, if I can run something at a really, really high temperature, I can get it to do something it might not do at a lower temperature. If you write like a Boltzmann factor, it's e to the minus beta u. So increasing temperature makes more states accessible to it.
Yeah.
And so at these higher temperature states, I'm accessing these more kind of high energy states more frequently, and I can observe properties that I wouldn't be able to observe otherwise.
Just look like this, maybe I should just, explain it like this. We all know that mechanical properties, right, are kind of related to molecular motion, right? So mechanical properties are related to molecular motion. So as we know in reaction kinetics generally, that increase in temperature increases the reaction rate, right? So now increase in temperature also causes increase in molecular motion. And since the molecular properties are related to molecular motion, so that means one can use like temperature to bridge the time scale. That's just like a simple explanation to it.
I like that. Yeah, simple is always better. Yeah. So I guess, which mechanical properties are particularly relevant and important to look at both, experimentally and computationally?
Yeah. So when you talk about mechanical properties, it depends on what, you want to gain from that project, right? From that, okay, what exactly are we trying to study? But in this case now, so the mechanical properties, we still look at the rheological properties, which are viscosity, elastic moduli, and viscous moduli.
So I guess we can even take a step back then. And when you say mechanical properties, what exactly do you mean by this?
So yeah.
Or maybe
So
I can rephrase the question,
okay.
in some sense, if you have a mechanical property that you're trying to look at, what kind of defines it, so to speak?
Yeah.
What would
So
make me say this is mechanical versus chemical?
okay. So when you talk about mechanical properties, right? So we know that mechanical properties are physical properties that a material exhibits upon the application of forces. So that's just mechanical property. You expect, when you apply a force, right, you expect some reaction from that material. It's just like okay, when you talk about, okay, let's say elastic material, right? If you pull it, well, if you apply a force and, you pull it, by the time you release it, it's going to go back. So basically, mechanical properties are just physical properties that a material exhibits upon the application of forces. That's just it. And when you talk about, like I said, elastic modular, modulus of elasticity, tensile strength, elongation, hardness, fatigue, all these are different mechanical properties. So that means for mechanical properties, you must have a force here applied, and the response to the force is what you're measuring.
So you have some type of mechanical perturbation, you observe what's going on. And the reason we care about this is because, we want materials to do different things.
Different things, yeah. So it now depends on what you want to use the material for. That will determine the kind of properties you will study, the mechanical properties you will look into in that case.
Yeah, you don't exactly want your car to behave like, Jello. If you get in an accident, you don't want it to just do blue, blue, blue. So
yeah, exactly.
But you want your Jello to behave like Jello. You don't want to be eating a car hood or something like that. Yeah. So let's kind of dive into the paper a little bit here. So you're looking at one particular ionic liquid. Oh boy. Maybe you can pronounce this for us, but it's bistrofluoride anion and 1-cyclohexylmethyl 3-methyl imidazine cation.
Yeah, so that's how it's been pronounced. So yeah, that's it.
That's a mouthful right there.
Yeah.
But okay, so you have this one ionic liquid that you're looking at, and so you're trying to look at the mechanical properties of this. So you're using MD. How are you mechanically perturbing this with MD?
So so basically for this we use the NEMD method, right? So that's the non-equilibrium molecular dynamics technique. So basically, so NEMD is just like a computer approach to cause deformation. So it's just a computer approach to cause deformation. So in NEMD, the system is perturbed, right? So if the system is perturbed, then the response is measured. So from the response output, one can now calculate the rheological properties that you want to acquire or that you want to get. So that's just it.
Okay, so you just have some artificial force on the outside that's pushing in on it, and just as you would with kind of an equilibrium simulation, you just are extracting different snapshots from it and averaging some property to get something out of it.
Yeah.
Okay, so with this fluid that you have here, you have kind of some glass transition, it appears from this. So why is it interesting to study this near a transition point, and what can it tell us more about this material in general by studying it there?
All right. So basically, when we talk about transition, right? So so when you talk about glass transition generally, so could you please repeat the question first?
Yeah, I guess kind of the question is why do we want to look at something near a glass transition, and what can it tell us about the material by looking at it there?
All right. So basically, when you talk about glass transition, okay, let's talk about let me explain this first by talking about the glass transition temperature itself. So you know, when you have, okay, okay, let's talk about glass to rubber transition itself. So I would like to explain, what happens in the rubber regime and glassy regime first, right? So in the glassy state, right, the molecules kind of exhibit limited molecular motion, right? So they kind of exhibit limited molecular motion. And basically, they sometimes they can say they are kind of frozen. They don't really move. Let me put it that way. In the glassy state, they don't really move. They are frozen, but they can only vibrate, right? So, but in rubber state, right? So, in basically a rubber state, the molecules can move freely, right? So they can move, and so the transition between rubber state and the transition from rubber to glass, from rubber regime to glass regime, that is what we call the glass transition temperature, right? Because when you measure at high temperature, that means at higher temperature, greater than the glass transition, we can say they're actually in equilibrium at that point. And what do I mean by equilibrium? In the case that, that's at temperature at the rubber regime, right? So, but in glass transition, in the glassy state, so the time scale of observation, right, is smaller compared to the time scale in which the molecule moves and relax. So that is basically why you want to study yourself at a temperature greater than the glass transition temperature. Because you can't really get, like I said, the time scale of observation is smaller in the glassy state. So compared to the time scale in which those molecules, because something that just vibrates, it doesn't really move at that point. So it takes a very long time for them to relax. So you don't want to take your property at a temperature below the glass transition temperature. So you want to go somewhere higher than the glass transition temperature, where the time scale of observation is the same as the time scale in which the molecules relax.
Yeah, so basically we don't want to be sitting there watching an ice cube. We want to be watching water actually kind of moving around, to take it very, very extreme.
Yeah.
Okay, so what exactly did you find that was interesting by studying this above the glass transition point?
Okay. What was it I will find interesting, right?
Or what kind of, what was kind of the big the first big thing, I guess, that kind of popped out to you when you first looked at this?
So basically, what we did, the main idea of this project is application of CCS, right, to that particular ionic liquid, to see if actually CCS can be applied to this liquid, right? So, from the paper itself, from the project, you will discover that we kind of created a master curve for viscosity, right? We created a master curve for the moduli. They're talking about the elastic moduli and the viscous moduli. And we created a master curve for the mean square displacement as well. So, and at the end of the day, for us to create a master curve, we need to have some shift factor. Remember, like I said, you are taking the property at different temperature and you are plotting them on the same graph, right? So basically what you're trying to do, you're trying to create just a single curve from those different curves you have created at different temperature, right? So, but for you to do this, there are some things that are required. That means you have to shift horizontally, right? So which is our horizontal shift factor, right? And you have to shift vertically too in some cases, which is our vertical shift factor. So by the time we did all these things, we created a master curve for viscosity, MSD, and elastic moduli and viscous moduli. We realized that we can actually use the same shift factor for all these three properties.
Okay, so it's kind of nice then. You really only have to look at one of the three. You don't really have to know all three.
Exactly. So this now means that, one thing about NEMD simulation is NEMD simulation is kind of time consuming, right? It is computationally costly as well. Let me put it that way. So instead of me, if I want to get like a shift factor for this particular ionic liquid, what this tells me is that I don't have to go through the stress of trying to get the shift factor from, from viscosity and elastic modular. Once I know it from MSD, because MSD is just like an equilibrium calculation, which is really fast. So that means you don't have to do the three. You can always get it from just MSD and you can apply it to the rest.
Yeah, so just to be clear, I guess by MSD you mean mean squared displacement, right? So you just look at how these ions are kind of pinging around.
Yeah, just the mobility of the ions. Yeah, exactly.
So can you give us any rationale then for why mean square displacement and the viscous moduli kind of seem to have this nice harmonious alignment in terms of their shift factor?
Yeah, I think basically because it's kind of rheologically simple. Sometimes they say when you talk about so when you talk about so when you say thermorheologically simple materials, so there are materials in which a single temperature dependent shift factor can be used to predict the transient thermal response. So basically, sometimes one of the reasons why people do this is that, okay, I understand that, okay, the question is the question is why do we have this, the shift factor for MSD, viscosity and elastic moduli, why are they the same? I mean, like they're almost the same, right? So I just believe it because because the system is a simple system. So if you're doing for a complex system, you might not get the same thing. So yeah, I think that's all I can say on that.
So yeah, that's kind of interesting. If you had a multi-component system, it might not all.
System. Yeah, exactly. Although there are some multi-component systems that this same principle has been applied. Like in our research group, we've done something like this for asphalt, and it actually works well. So, but some multi-component system, it might not actually work well. So, basically, yeah, for some multi-component system, it might not actually work well. So, basically, how can we know that if this will work well for a particular multi-component system? So, if the components of the multi-component system are similar in shape and chemistry, so there's a high tendency that CTS principle would work. But, like I said, for example, asphalt, we did it in our group for asphalt and it worked well. But if the chemistry, or they are not similar in shape, they are not similar in chemistry, then CTS might not work for such multi-component systems.
Yeah, I guess if you kind of have multiple methods that be competing with one another, if you raise the temperature of something, they might start, butting heads a little bit more.
Exactly. So they're going to react different way, but if they react the same way, so then basically it's more.
Yeah, I guess you could kind of draw the parallel as if you're driving in the car with your brother or something, and the AC is on, you're both sitting there perfectly happy. But if it's really hot out, your temper's going to flare super quick. So there might be, some scuffling in the back seat that someone winds up with a black eye or something. So you can't exactly extrapolate if you have multiple interactions that could be going on.
Yeah.
But you guys did see kind of, I think, some interesting behavior here where you have different shear viscosities at different temperatures. So it looks like, you kind of have Newtonian fluid, and then as you increase or lower the temperature, you wind up getting kind of more shear thinning behavior. Did you kind of touch on that a little bit?
So you're talking about the viscosity part, right?
Yes, that's the one.
Okay. So let me go back to that paper just to make sure. Okay. So you were talking about
yeah, I think it's figure 7 to be specific.
Figure 7, right? Yeah.
Yeah. So essentially you kind of have some shear viscosity that you see, and that's plotted as a function of the shear rate. And at different temperatures, you see kind of a different response out of that. So could you talk about that some?
So basically, right, so like you just said, so we have a plot of the viscosity against the shear rate, right? So, and we measure the viscosity at different temperature, right? So one would see that at 300 Kelvin, right, we're able to get a plateau, right? And we're able to observe the, shear thinning region, right? So the same thing happens to at 340, a little bit. Then I think for 380, something a little bit. So, but for 420 and 460, right, we were, no shear thinning region was observed, right? So that tells us that those frequencies, those shear rates rather, in which we have studied the system, so we might for us to experience like a shear thinning region, right? For us to experience like a shear thinning region for those other two, which is 420, 460, we might have to go to a higher frequency. When we talk about frequency is like the opposite of time, inverse of time, right? So that means that it's a short time. So, right, so and they are inversely proportional, like I said. So that means high frequency means short time, right? So for us to actually get like a thinning region for all those two temperature, right, we might have to go to a very high frequency as well.
Yeah, you need to find some way to have it quicker than the temperature time scale.
Yeah.
Very nice, very nice. So I guess even before we kind of talk about the next thing, so, what exactly can we talk about these fluids when we go from more of a viscous response to an elastic response? What kind of changes can we observe going on with it?
Right. Okay. Yeah. So thank you. So as we all know, let me start by explaining this. For elastic response, right? If a force is applied to an elastic material and then removed, what will happen? It goes back to its original position, right? That's for elastic.
Kind of like a rubber band, right?
Yeah,
we
like just like a rubber band,
right
like
back.
a spring, right? Yeah. So, but for a viscous fluid, when the force is applied, it continuously deforms. And then when the force is actually removed, it doesn't go back. So basically, elastic materials are used for storing energy. So that means, for it to go back, that means some energy, right? In that process of applying that force, the energy has not been dissipated. That's for elastic material. The energy are stored, right? So, but for viscous material generally, so, the energy are being dissipated or absorbed in this case, right? So when you talk about, so for elastic response now, so for elastic response, so basically that is, I don't know if I answered the question with
Yeah. I guess it's just kind of a way of saying that, I just kind of wanted to get some feeling for the difference between an elastic and a viscous response.
Exactly.
So an elastic is kind of energy conserving in some sense.
Yeah, exactly.
And viscous is you're dissipating it out, whether that's through heat or some other motion going on.
Yeah.
And so what do we typically, or I guess in case for this particular fluid, as we get to higher and higher frequencies, what exactly do we see in terms of this material?
So yeah, in this case now, at higher frequency, right, it becomes more elastic, right? So it is more elastic. I said the other time, that frequency, it's like inverse of time, right? It's inverse of time. So it's more elastic at higher frequency because it is at a short time. So at high frequency, the molecules do not have enough time to relax, and they act as elastic. That's just the main reason. So they do not have enough time to relax, and they act as elastic. So that's just it.
So it's kind of like if you take a piece of bamboo and you just push it really hard, it's going to snap right back up to the top.
Yeah.
Okay, interesting. And so we can basically, what we're trying to do is try and take this time, temperature, superposition and kind of probe these properties, because it can take a really long time to observe kind of this more viscous
Yeah,
response where things kind of
yeah,
nestle down into their nice sweet spot.
yeah.
Okay. So I guess, can you tell us how specifically you try and compute these different shift factors then?
All right. So yeah, so for us to compute like shift factors, yeah, like shift factor, let me start with the horizontal shift factor. So horizontal shift factor, like I said, I don't know if I mentioned this earlier, is just the difference, the relaxation time between the temperature you're considering and the reference temperature. That's what horizontal shift factor is. So remember, we're plotting the property against frequency, or it could be against time itself. So as you are shifting horizontally, so that means on the scale of time, time is the one that is the horizontal, right? So it's just like, like I said, horizontal shift factor is just like a difference in the relaxation time between the two temperatures. I mean, at those two temperatures, right? So
So I'm
now,
just moving along the axis
yeah,
based on the
exactly.
temperature.
So that's just horizontal. The vertical, you are moving along the y-axis. So basically, but there are ways to go about this. And the way you compute your shift factor even depends on the system you're actually considering as well, right? So to some extent, it depends on the system you're considering. So so basically, okay, let me start with this. Okay, for horizontal shift factor, I'm sorry, for vertical, let me start with vertical, right? So in the case of, viscoelasticity of unentangled polymer melt, I mean, one can calculate the horizontal shift factor by, multiplying the reference temperature, the temperature, the reference temperature by the density at that reference, the temperature of that material and the density at that temperature. Let's say, for instance, okay, my reference temperature is basically 300, right? So, and I have the material property being measured at 350. Then I want to shift from 350 to 300. So in this case now, my reference temperature is basically 300, right? So, but I'm trying to shift from 350 to 300. So in that case now, I need to calculate my vertical shift factor. So that will be temperature that I want to shift, the temperature of that material, I mean, like the temperature at 350 times the density of the material at a temperature of 6. Oh, sorry. I'm so sorry for that. I think I missed that. I missed that. I'm trying to actually simplify this. So I don't want to make it abstract. I'm trying to simplify. So, like I said, I thought my reference temperature is 300, right? So my reference temperature in this case is 300. And I'm trying to shift and have the property measured at 350. And I'm trying to shift from 350 to 300. So in this case now, to compute my vertical shift factor, so that will be temperature that I want to shift to. That means the temperature of the material, I mean, at that point is 300, which is the reference temperature. Then the density as the reference temperature, the density of the material at the reference temperature, I'm going to multiply them together, then divided by the temperature in which I'm considering to shift down to 300, and then multiply by the density of the material at that 350. I don't know if I was able to explain that well, dude.
Yeah, so basically it sounds like you just need to know the density and the temperature
Exactly.
at two different
Exactly.
temperatures, and you're taking the ratio of them to get this shift factor.
Exactly. That is for the vertical shift factor. Now, for the horizontal shift factor, basically, that I mean, depending on the type of this thing, you can do manually. So people just shift manually and say, okay, and see where the stuff aligns with the other.
Is there any type of is it kind of unique in how you shift it, or are there kind of multiple solutions that can kind of pop out of it? Basically, can I get multiple shift factors that all appear to be correct?
I mean, for a certain temperature, remember one of the conditions for us to even, we said they must have the same, I said one of the conditions again, sorry, hold on. I'm trying to, so I said they must have like exact matching state of adjacent curve, right? So when you say exact matching state, so that means if I have measured, let's say, we've done it at different frequency, right? So we have the starting curve. So that means if I'm shifting from 350 to 300, so I'm just going to have one shift factor for that temperature, shifting from 350 to 300. It's not going to be multiple shift factor. It's going to be one for the horizontal shift factor, one horizontal shift factor, and it's going to be one vertical shift factor in order to move from 350 to 300.
So yeah, it's a unique number that you get popped out of it.
Exactly.
I guess that makes sense, right? You're not having any more collective motion that pops out of it. So it should be more or less the same curve.
Exactly. So, and if I'm considering maybe another temperature, so let's say maybe I have my property at 400 degrees too, if I want to see, so that one too, we have its own unique shift factor. So you get different unique for different shift factor at different temperature.
Okay. So I guess kind of, now that we see that with kind of this material here, instead of trying to do, NEMD, we can basically try and run equilibrium MD, which is much, or I'm not going to say it's easy to converge, but it's easier to get good statistics out of than NEMD, because we no longer have this time dependence coming out of it. So kind of with this MSD now, what do you want to study with next? Or what do you want to study with it next?
Oh, with the ionic liquid or?
Yeah, now how do you want to take kind of the knowledge that you got from this study and apply it to something else?
Yeah. So basically, like I said, it's just like, like I said, the major idea about this project is the time temperature superposition. That's what we're proving, right? So, I mean, maybe next we can consider another system that is more complex than ionic liquid and see how how CCS2, whether it's going to work or not for it. So that's, next for this.
Yeah, it would certainly be interesting to make, predictions across a broad swath of different ionic liquids and see if you can experimentally back it up. So I guess kind of wrapping up then, if you were to go back and restart this from kind of square one, what exactly would you do different? Or what, if anything, would you do differently?
If anything was, let's see. What exactly would I do different? I'm not too sure about that for now.
Maybe in 5 years you'll know.
Okay, so let's say I want to, or maybe I didn't get a question. I said, okay, let's say I want to revisit this project, right? Then what exactly, what, if anything, what would I want to do in a different way, right? That was the question, right?
Yeah, would you try and take a look at something else? Would you have focused in on something earlier on? Or, what do you think could really make this study kind of more robust?
Okay, maybe, probably, one might want to, right now we only consider, let's say, we thought like the viscosity, right? We talked about the elastic modular and all that. So maybe we can compute like some other properties as well. So probably maybe we can compute some other properties and see if it's still going to be the same, right?
Yeah, like you could try and go after heat capacity or something like that.
Exactly, yeah.
Okay, so I guess, is there anything else surprising about the study you want to talk about, or anything you want to mention we haven't touched on yet?
Yeah, so okay, let me just quickly say this, right? So, one thing we didn't just run the simulation, we actually compared it with experimental data that we have as well. So we compared because we compared with experimental data because I think another research group in our school So they kind of, study this particular ionic liquid too, where they computed the elastic moduli, viscous moduli, viscosity. So we kind of compared our results with this as well. So, but I said something earlier that, there's a time to discrepancy between experiment and simulation, right? So there's kind of a mismatch in time scale. So, and one thing about simulation is that one thing we normally do, now due to time scale in simulation and experiment, the CG, that's the glass transition temperature. The glass transition temperature in simulation is always higher compared to experiment. So because of this, right? So there was the mismatch between the results we got, like when I say discrepancy is the there was kind of the discrepancy in the viscoelastic property results that we obtained from simulation and experiment at given temperature. So in order to account for this mismatch, actually, so we kind of, calculated like a rescaling factor. So that rescaling factor was calculated, and that was actually used to, the rescaling factor was used, this rescaling factor was used to do the shift in order to have a match between the experiment and simulation, right? So this, like you said, so we use like the WLF equation. So this parameter that we use from WLF is, I think WLF is, I don't know why I think it's in the paper. So I don't want to pronounce the wrong thing. Yeah. So it's William Landau Ferry, right? Equation. So it's William Landau Ferry equation. So we use this WLF equation, right? So kind of calculate this rescaling factor. So with this rescaling, but there are these parameters in WLF. So we can, there's a universal parameter, and there is in the experimental work as well, they were able to get like the parameter itself, but we couldn't use the universal parameter. Basically, the when we tried using the universal parameter, so the experimental massacre was allowed to kind of reduce compared to what we have. So, but when we use the the parameter, the WLF parameter that they calculated in that paper, so we were able to kind of calculate the rescaling factor, which kind of enable us to be able to match both the experimental and the simulation.
So why do you think there's this discrepancy in the glass transition between the experiment and the theory? Do you have any like molecular understanding of it?
Yeah, it's just the time scale. Like you said, simulation is being measured at a very low time scale compared to lower time scale compared, to experimental. So it's just basically because of the time scale difference.
So in principle, if you were to just run your simulations for, 15 years, you should get the same glass transition then?
Exactly.
And so do you think that would help your final curves to collapse better to the experimental curves then? Instead of having to use WLF factors, you could use like verbatim direct comparison?
Yeah, but that's good. We know that's not possible for now, right? Because, yeah, so that, like I said, we said earlier that maybe in the next 15 years, probably we'll probably have, like that computational ability to run simulations for, let's say, seconds and times, to match the experimental time scale.
Yeah, I think we're getting closer and closer with each passing year, so hopefully soon. But okay, anything else you want to comment on?
That's all for now.
For now, until the next paper comes, then we can,
Yeah,
then we
until
can
the
chat
next paper
again.
comes out. Yeah, exactly.
All right. Well, thanks for being on the show, Adegbola, and thanks for
Yeah,
tuning
thank
in,
you for
everyone.
having me on the, yeah, thank you for having me on the show as well.
No problem.